Well, we have these results from earlier in the problem, that the velocity for the hanging mass is the square root of gd, and that the work done by gravity as the rope falls is mgy squared over 2l. So now they're going to ask us, what is the speed, v sub r, of the rope as it falls? Well, we're going to do just the same thing we did in part A. We're going to say that the kinetic energy is equal to the change in potential energy. And so once again, the kinetic energy is 1/2 mv squared, or in this case, 1/2 the mass of the total rope, because the whole rope is moving, so that's m, times v sub r squared. And that has to be equal to the change of potential energy, which is the work done by the force of gravity. So we're just going to put that in there, mgy squared over 2l. And the m's cancel out, the 1/2s cancel out, and I get v sub r squared is equal to gy squared over l, or v sub r is equal to the square root of gy squared over l. That's part D. Then in part E, they ask you to compare the velocities when the thing on the table is all the way off. So, for the rope, when y is equal to L is when the rope is all the way off the table, right? So we just substitute in, instead of y in this equation, we're going to put L. So the velocity of the rope in that case would be the square root of g times L squared divided by L, which is equal to the square root of GL. And then for the hanging blocks, what we're going to do is we're going to say that D, the distance in our hanging block equation, this one here, is going to be equal to L. So that means that the velocity of with the hanging blocks is going to be the square root of GD, which is equal to the square root of GL when D is equal to L. And as you can see, these two things are equal.